Now that we are comfortable with isoelectric points in the PI, in our previous video we actually calculated the isoelectric point for two amino acids. One was histidine, the other one was aspartic acid. How about we calculate the isoelectric point for not an individual amino acid, but maybe 4 amino acids joined together to form a tetrapeptide, AYDG. Okay? So that would be the goal of this video tutorial. How do you calculate the isoelectric point for this 4 amino acid peptide, also known as a tetrapeptide of AYDG? Well, first of all, do you know what AYDG stands for? Okay, this is super important. Otherwise, it goes back and harkens back to the need to memorize those one-letter amino acid abbreviations. A stands for alanine. Y stands for the amino acid tyrosine. D stands for the amino acid aspartic acid. Okay, aspartic acid, or if the proton is off, aspartate. And then G stands for the amino acid glycine. Okay. So what is the isoelectric point for this tetrapeptide AYDG? Before we go ahead and actually calculate the PI for this tetrapeptide, I want to draw the structure of AYDG, flat, one-dimensional structure. Okay, so this would be important on your exam, where you'll be given a tripeptide, tetrapeptide, or a peptide, and you'll be asked to draw the structure atom by atom. So this is how we'll do it atom by atom. What is the side chain of alanine? Okay, that's the methyl group. And then what comes next? All right, what comes next is our peptide bond. Okay, remember the N to C polarity in a protein polypeptide chain. Okay, what is our next component here? We've got alanine as our side chain. Our next component is the side chain of tyrosine. Do you know what the side chain of tyrosine looks like? Okay, the side chain of tyrosine looks like this. All right. So we have our alpha carbon, alpha amino group. What's bound to the alpha carbon besides the alpha amino, side chain, and alpha H? Okay, it's going to be the alpha carboxylic acid, but its peptide, it has a peptide bond with our third amino acid, which is aspartic acid. So what is the side chain of aspartic acid? Now, this question leaves a lot to be desired, because I'm not giving you the pH at which we want to devise the structure of AYDG. But let's say if it's a completely protonated pH, this would remain protonated. All right. So at physiologic pH, this will actually be gone. Now let's move on. We finished the side chain of aspartic acid. So what is next? All right. So alpha carbon, alpha amino group. The alpha carboxylic acid is in a peptide bond with our last amino acid, and that is glycine. All right. So that is actually the one-dimensional structure of this tetrapeptide. On an exam, okay, you'll be asked to draw a box around the peptide bond. So if it asks you to do that, you can draw a box around your peptide bonds like this. Okay, label the alpha carbon, so that would be the alpha carbon for alanine. This would be the alpha carbon for tyrosine. This will be the alpha carbon for aspartic acid, and this would be the alpha carbon for glycine. And maybe a couple of other variations. Maybe label the side chains or draw a square around the side chains or a circle around the side chains. So if I were to ask you to draw a circle around the side chains, you would draw the circle around the side chains just like this. And phi and psi angles. So if I were to ask you to label the phi and psi angles, how would you be able to do that? I would pick an alpha carbon, any alpha carbon. I'll pick this alpha carbon. The alpha carbon to the C carbonyl group, C double bond O group, that is the angle that's defined by psi. The alpha carbon with the NH group, this bond rotation defines the amino acid psi. Okay, so this would be phi, and this would be psi. So once again, the alpha carbon to the C double bond O is psi. The alpha carbon to the NH group is phi. Okay, so on an exam, you should be able to just regurgitate that out. If you have the flashcards, the side chains should be very easily regurgitated from your flashcards. However, I cannot emphasize this enough that you really, really need to memorize these amino acids. Okay, if not now, definitely it's going to come back to haunt you if you don't memorize those amino acids. I speak to all the pre-meds and pre-PA students and pre-dentists and all the pre-professional students. All right, so that would be one answer. I would also ask you, what is the structure at pH 7.4 or physiologic pH? All right, so this structure here is the fully protonated form. If I were to ask you its predominant structure at physiologic pH, it's going to be a different answer. Okay, so just drawing it over again. At physiologic pH, you're going to have to look at the pKa's. All right. And which pKa's come off at a pH of 7.4, or another way of saying it, this is which protons come off or have a pKa that will dissociate at a pH of 7.4. All right, so that one will come off. That one comes off at around 4, side chain of aspartic acid. And then this one will come off. Okay, this one comes off at around alpha carboxylic acids from glycine, or alpha carboxylic acids from amino acids generally come off at pH of 2. The side chain of aspartic acid comes off at a pH of 4, so that one's definitely going to come off at pH 7.4. This one stays. This one has a pKa of around 10. And the alpha amino group stays, that proton stays, that has a pKa of around 9. Okay, so if you're asked to draw the predominant structure at physiologic pH, okay, this is what the structure would look like. Okay. This is what the structure would look like. The only difference being is now this proton is gone and this proton is gone, because this proton leaves having a pKa of around 2-ish. This pKa, side chain of aspartic acid, has a pKa of around 4-ish. This one has a pKa of about 10-ish, so it stays. This one has a pKa, the alpha amino group has a pKa around 9-ish, so that one's going to stay at pH 7.4. Right, everything else remains the same. Okay, so just be comfortable to do that on an exam. Consult your flashcards. Now let's get to the meat of this problem, how to resolve for the PI of AYDG. So this is how I do it. First of all, you're going to need to get all your pKa's in order, kind of like you need to get all your ducks in order if you ever want to do anything. So get your pKa's in order. The second thing you want to do is remember what I said before. Okay, you want to start with the completely protonated form of the molecule. In this case, the molecule is not a single amino acid. The molecule is a tetrapeptide, AYDG. Okay? This is how I solve for PI problems. Okay? You notice that the peptide bond, there's nothing ionizable about it. The peptide bond does not have a pKa associated with it. So all I have to do is draw my alpha amino group of the first amino acid, draw my alpha carboxylic group of my last amino acid, and how many side chains do I have? 1, 2, 3, 4. And then I'll just draw my side chain. So alanine side chain is CH3. Aspartic acid side chain is, tyrosine side chain is CH2. Benzene OH. Aspartic acid side chain is CH2, COOH. And then glycine side chain is H. All right. So now, notice I didn't add anything with regards to the peptide bond. It's just everything that I need to calculate the PI is in this form. Okay, I omitted the alpha carbon and I omitted the alpha hydrogen. All right. Now I get my flashcards and I start ticking off protons as to when they come off according to their pHs. So using my flashcards and using my notes, I find that, let me draw this down here, that at a pH of 2.35, this proton comes off because this has a pKa of 2.35. The alpha carboxylic acid group of glycine has a pKa of 2.35, so at a pH of 2.35, this will start to come off, and I'll have this form of the structure. This side chain stays the same. This side chain still remains the same. Let me zoom out. This side chain stays the same. This H stays the same. This proton comes off. Okay? So now, here I have a net charge of, well, I'm zwitterionic. Very good. Okay? I'm zwitterionic. What's the net charge here? The net charge on this guy is +1. What's next? All right, according to my flashcards, the next one that comes off is at a pH of 3.90, and that is going to match the pKa of the side chain of aspartic acid, which has a pKa of 3.90. So at 3.90, that pH, this side chain of aspartic acid begins to come off. So then I'll get this structure. Okay, notice this proton has come off now. This stays the same, and this one stays the same. Okay, so this is the side chain of glycine. This H is the side chain of glycine. That doesn't come off. Make sure you know what protons come off and what protons do not come off. Okay, that's just organic chemistry there. All right, so what's the net charge on this molecule here? The net charge on this molecule is -1. Let's continue forward and move on here. What's the next proton to come off? The next proton that actually comes off, according to my flashcards and that I have, the next one that will come off will be at a pH of 9.7, because this proton, one of the protons in the alpha amino group, has a pKa of 9.87. So when that happens, this proton begins to come off, and you'll get this structure here. The CH3 stays the same. The CH2 benzene ring OH stays the same. The CH2COO- stays the same, and then that H from glycine, nothing happens to that. So now we have a charge of -2 to the molecule. And then that is not it. We have one more ionizable proton, and that is this one. So let's move our arrows up, and that one comes off, begins to come off at a pH of 10.46. At a pH of 10.46, at a pH of 10.46, you match the pKa of this proton on the side chain of tyrosine, which is at 10.46, and you get this structure here. CH3, CH2, that proton begins to come off. Here you have a CH2COO-. Here you have an H. Here you're going to have a charge. The net charge of this entire molecule is going to be -3. So as we zoom out here, we have taken this tetrapeptide AYDG and we've just ran it through the entire gamut. At 2.35 pH, this proton begins to come off. At 3.90, that pH, the side chain of aspartic acid begins to come off. At pH 9.87, the alpha amino group, that proton begins to come off. And at 10.46, the side chain of tyrosine, that proton begins to come off. Okay, so then you're going to start getting this structure. 10.46, at that pH, this proton begins to come off. That OH is stripped, that becomes an O-. So what is the PI, the isoelectric point of this tetrapeptide? Okay, the isoelectric point is defined as the pH where the zwitterion dominates. The zwitterion is located right here. The zwitterionic form, and that is going to be flanked by this pH at 2.35 and then this pH at 3.90. Okay, so 50% of the zwitterion exists at pH 2.35 along with this guy. And at pH 3.90, 50% of the population of this tetrapeptide exists here, and the other 50% exists as that guy. So the PI for this AYDG tetrapeptide, alanine, tyrosine, aspartic acid, and glycine joined together via 3 peptide bonds is going to be 2.35 plus 3.90 divided by 2. And then doing that in your calculator, let me do that in our calculator here. 2.35 plus 3.90, about 3.13. So at a pH of 3.13, the zwitterionic form of this tetrapeptide dominates. Okay, so that population, this population, begins to dominate at a pH of 3.13. Okay, so this is how you want to proceed in doing your PI calculations, notice you start with the completely protonated form, and I avoided all of this mess. I avoided drawing all of this structure. Okay, I only concerned myself with drawing the alpha amino group, the alpha carboxylic acid, and any side chains. So if you're given a question on the exam where you're asked to calculate the PI of AYDG, just start from here. Okay, just start from here. Start with the fully protonated form of the molecule. In this example, it was the tetrapeptide, and then start ticking off protons according to their pKa values. Okay, start ticking off protons. Tick them off one by one according to their pKa values. Find the zwitterion and average the pHs that flank the zwitterion. Okay, so that's how you want to approach these types of problems. I've seen students do all sorts of things that sort of violate this. I've seen students actually start from here and then try to pull off protons. I've seen students pull off the wrong protons. So you don't want to do that. Okay, you want to know what protons come off at what pKa, so that as you increase the pH, figuratively, not literally, as you increase the pH, you know what protons come off, and you know which one is the zwitterionic form. Okay, so make sure you know and are comfortable with calculating PIs of tetrapeptides, maybe a pentapeptide, tripeptides, like that for the exam. Obviously, if you're going to calculate the PI for a 50 amino acid protein or 100 amino acid protein, that's going to be impossible, right? But there's computer programs out there on the internet that actually do that for you. PIs is very important. You kind of want to know that information, perhaps if you're interested in drug design or a drug that's going to target a protein. So it's generally used a lot by big pharmaceutical companies. And it's just good to know if you're doing research on a biomedical protein such as hemoglobin or carbonic anhydrase or superoxide dismutase. It's important to know you change some amino acids here and there. Does the PI change? Is it compatible with the physiologic pH of the cell? So I want to hopefully convey to you that these types of calculations do have an importance and do have a realm of relevance, especially if you want to focus more on proteins and drug design and drug development. Okay.